Large language models operate under a rigid computational limit, autoregressive text generation. They process data sequentially, performing a full forward pass through billions of parameters to output exactly one token at a time. Because every word requires the model to crunch its entire weight set, producing text one token at a time is highly inefficient for modern hardware. This illustrates the engineering goal. On top, we see the standard sequential progress. On the bottom, entire sequences of data pre-populate ahead of the current generation point. To increase inference speed, developers must move toward systems that predict multiple tokens simultaneously. This evolution led to an architectural shift called multi-token prediction, or MTP, which brings us to the recent release of Google's Gemma 4 open-weight models. Gemma 4 was trained with MTP to enable significant speed gains. However, Google removed the MTP code blocks from the standard public release weights used by most developers. By deconstructing the evolution of speculative decoding into MTP, we can see why the specific speed optimization is technically incompatible with current open-source software. The missing code in Gemma 4 reveals a structural lag between the latest model research and the tools we use to deploy them. Speculative decoding was the first solution to the autoregressive bottleneck, splitting the workload between two systems. The small draft model runs ahead, rapidly generating a sequential array of tokens. The large primary model then evaluates this entire sequence concurrently in a single forward pass. If the primary model confirms the predictions are mathematically accurate, the user receives multiple tokens for the computational cost of generating one. If a predicted token is rejected, the sequence halts. The incorrect token is discarded, and the large model calculates the correct next step to reset. This dual model setup requires an absolute mathematical constraint. Both models must share an identical vocabulary mapping. LLMs do not predict words, they predict integer token IDs. If the draft model predicts token ID 42033, the primary model must map that specific integer to the exact same text output. If the models use different tokenizer vocabularies, the verification layer fails and the system produces nonsense. While speculative decoding bypasses the single token bottleneck, its reliance on two discrete models running in memory creates rigid constraints for deployment. The next iteration, speculative decoding, pushes this further. Instead of a single line, the draft output fans out into a branching probability tree, computing nested possibilities ahead of its state. The primary model evaluates these branches simultaneously, pruning incorrect paths to validate one sequence. By pre-computing alternate outcomes, the system ensures that a single rejected token doesn't cause a total halt in production. However, this approach increases the computational load on the small model, which raises its error rate. Statistical drift in the draft model compounds quickly. This forces the large model to reject entire branches, which eventually degrades system performance. SSD shows the limit of external drafting. Optimizing a secondary model eventually hits a ceiling due to memory overhead and error drift. Multi-token prediction is the structural solution. The separate drafting and primary layers merge into a unified system with multiple internal output heads. Internalizing the speculative decoding process removes the secondary model. The primary model uses internal routing to natively project multiple tokens forward simultaneously. This allows developers to load only one model into VRAM, reducing total memory requirements. Because the drafting logic shares the same weights and vocabulary as the primary engine, mapping conflicts and error drift are effectively removed. MTP provides a constant speed boost without the complexity of managing two different models. This marks a shift toward monolithic architecture-level optimization, which creates a problem for general-purpose software. Internal routing makes MTP highly architecture-specific. Without a perfectly matched environment, the model cannot properly communicate its predictions to the software. General-purpose inference engines are built for standardized model structures. When an MTP model attempts to plug its complex output nodes into these generic framework slots, the logic cannot align. Standard engines expect a single sequence of layers, which contradicts custom internal routing. Forcing these tools to support MTP requires developers to write custom code adaptations for nearly every new model that uses it. This integration friction drove Google's engineering choice for the public release of Gemma 4. To ensure the model would work across the open-source ecosystem immediately, Google stripped the MTP code from the standard gguf and safe tensor files. The fully optimized MTP version was exclusively preserved in precompiled formats built for LiteRT. LiteRT is Google's own edge device framework, specifically designed to handle the complex internal routing that generalized software cannot yet process. Removing the MTP code wasn't a matter of hiding performance. It was a compromise required to prevent mass software failures across incompatible open-source tools. Adoption rates clarify the impact of this choice. Millions have downloaded the standard Gemma 4 models, while the LiteRT versions have approximately 8,000 downloads. This shows that the developer community prioritizes modular compatibility over isolated speed optimizations. The industry has evolved from the single token bottleneck to the dual model logic of speculative decoding, and finally to the unified architecture of multi-token prediction. Internalizing crafting logic within the model weights is the trajectory for high-speed inference. The release strategy for Gemma 4 is an example of a structural gap between model architecture and deployment software. Open-source infrastructure is currently catching up to the innovations of model researchers. Until generalized inference engines support bespoke MTP routing, these speed optimizations remain restricted to specialized, proprietary deployment environments.